Hello. Today we're going to be using a particle simulation to try to understand rates of reaction, why some reactions are fast and other reactions are slow. This lesson is going to be a little bit different. The simulation I'm using does not run on Chromebooks since it uses Java. So if you have a Windows computer, then you can download the simulation yourself. Otherwise, you'll have to use this video. I recommend going through and pausing after each question. I will be reading the question, doing something with the simulation, and then that's when you should pause it and write in your answer, and then I'll go on to the next question. Okay, so rates of reaction. Some reactions are fast, like combustion, burning. Other reactions are slow and take a long time, like rusting on a car. Why is that? And what actually needs to happen at a atomic level for a reaction to happen. So we're going to be using this simulation over here, and the first place I want you to look at is at the bottom. Number one, looking at the bottom, what type of reaction is this? So we have an A alone by itself, a single A, hint, and it reacts with a BC compound, and over on the product side, the A has partnered up with the B, and now the C is alone. So number one, which type of reaction is that? Synthesis, decomposition, single replacement, or double replacement? Okay, so to get this reaction started, this is very fake. In real life, there's no plungers. It's not like we're gonna pull this back like it's a pinball machine, which is unrealistic, but it allows us to control the speed of the particles. So if I pull this plunger back just a little bit, you just write down what you're seeing. What happens if you only pull it back a little bit? Do you think you see a reaction happening? And by the way, this is a lot of what do you think and what do you see? Don't worry about being right or wrong, just write down what you see. Tomorrow, there'll be notes and stuff, but I want you to learn as much as you can from the simulation now. Okay, so that's number two. What if we only pull it back a little bit? So now I'm going to pull it back a lot. And it looks different. So how is this different than before? When we give it a lot of energy, how is this different than before? So one more time, here's just a little bit of energy. So this word effective, when we talk about an effective collision, these particles collide with each other. If it's effective, we should see a change happening. This change that's down here at the bottom of the screen. This is the reaction that'll happen if we have an effective collision. So at least when it's going slow, are you seeing an effective collision? What about when it's going fast? Do we see effective collisions now? Are you seeing changes? All right, question 4. If you look at this reaction, you'll notice the arrow goes both ways. So the top part goes forward, the bottom part goes backwards. That means the reaction is reversible. What does this mean? Now you could Google this, but you can figure it out based just on your observations. So reversible sounds like reverse or going backwards. So we have a reaction that goes forward. If you notice how they're colliding with each other, we have a change, but then it bounces and it changes back. So the reaction's going forwards and backwards, forwards and backwards, forwards and backwards. You can put that into your own words. All right, number 5. What happens if you change the angle of the shot? I'm gonna go over here to angle the shot. And when I pull this back, I'm going to give it enough energy that a reaction would happen, but I'm going to hit it on the side. Did a reaction happen? Did you see a change? Let me reload the launcher. Let's try it again. Let's hit it on the other side. Was that an effective collision? We'll do one more. Let's send it way off to the side. So no reactions happening because we're not having any collisions. This is a key idea. Oh, was that an effective collision? No. All right, so that was 5. What happens if you change the angle of the shot? All right, what happens if you increase the temperature? So we'll keep this going. Let's raise the temperature. What do you see happening? Looks like they're about ready to, oh, yep, we're about to break the simulation. So that's if we raise temperature, and what happens if we lower the temperature? This probably doesn't surprise you since you saw this behavior before in other simulations, but it's a good reminder at an atomic level what it means to raise and lower the temperature. Okay, on to number 7. All right, so we're going to switch over to many collisions because in the real world, we have many more than just one atom of each type. So I'm going to put 10 A's and 10 BCs into the chamber, and we'll see if we have any reactions. Now, if you look, the total average energy, the temperature is pretty low, and the average energy is low. We'll talk about what this blue shape means later in another unit. So the question is there a reaction happening in the chamber right now? Are these collisions effective? And explain how you know. So one thing I notice is there's one little C bouncing around free. You can think about what that means. Did a reaction happen? Are reactions continuing to happen, etc.? So that was 7. Is there a reaction occurring? Explain how you know. Number 8, let's increase the temperature and see what happens. So I'm going to heat it up. Particles get faster. And as it gets harder to follow the particles and how they're changing over here, you can always look over on the right-hand side and look at the numbers, and they'll tell you how many of each there is. So I'm going to raise the temperature up just a little bit more. Are we getting chemical reactions now? How does the number of reactions compare to before when it was a low temperature? And I'm watching these numbers over here. Okay, on to number 9. What happens to the number of effective collisions if you increase the amounts of the 2 reactants? Okay, so we showed how increasing temperature affects the number of effective collisions. Remember, an effective collision is every time a reaction happens. Basically, every time these numbers change, we know that a reaction has happened, which means that they collided effectively. So I'm going to pause this, and instead of 10 of each, I'm going to go up to 100 of each. A lot. And let's see what happens. So we've got craziness happening over here. By the way, this is much closer to what it's like in real life. There's, trillions and trillions of atoms all in motion, colliding with each other. And look at how fast these numbers are changing. So number 9, what happens to the number of effective collisions if you increase the amount of the reactants, like we just did? Number 10, what is the relationship between the temperature and the number of effective collisions? I'm going to lower this back down to a low temperature. Whenever a question says, what is the relationship? Your answer is always going to be in the form of as blank increases, decreases, or stays the same. So in this case, your answer is going to be as the temperature increases, the number of effective collisions either increases, decreases, or stays the same. That's your tip from Sweeney. So you can look over here, but that's kind of crazy. I'd look over here at the numbers, look at how fast the reaction is happening, how often these numbers are changing. That tells you how many effective collisions are happening, and watch what happens as I increase the temperature. So that's about halfway, and now all the way. So as the temperature increases, what happens to the number of effective collisions? And finally, number 11, with this understanding of the particles in your mind and thinking back to the videos you saw yesterday of the Alka-Seltzer tablet dropped in water, why did that reaction go faster in hot water as opposed to cold water? And I want you to use the understanding you've developed from this simulation. 12, and I think this is the last question. Explain what you need for an effective collision in your own words. So I'm going to take it back as a reminder. I'm going to go back to single collision here. There was 2 main things that we looked at. In order for this reaction to actually happen, in order for the collision to be effective, we needed 2 things. So the first thing related to that was not an effective collision. But this is an effective collision. Why? So that's one thing. What was one thing we needed? The other thing we looked at was this. If we change the angle, not an effective collision. But if we hit it in just the right spot, that was an effective collision. So in your own words, what are the 2 things we need for a collision to be effective? I hope that you're able to use this to answer the questions. I wish this could be like an interactive type thing that we did in class, where if you had questions, we could go through it right away. I miss you guys. I hope you're doing well. And let me know if you have any questions. All right, take care.